Hey, welcome back. So we're continuing these 99 Haskell problems. In the last video, I got quite stuck on the ninth problem, but we have the solution now. I had to look at the answers. Hopefully that won't happen again. It will, but you know. But I'll explain what we have. So what we're trying to do here is okay. So we're trying to pack consecutive duplicates of list elements into sublists. So if we're given a list, it looks like has a bunch of duplicates and then other duplicates, then we want to turn this into a list that looks like this. So what we're doing here. So as with most of these, if it's an empty list, we just return the empty list. Then if it's not an empty list, we take the first element. So we split the list into the first element and the rest of the list. That's what this pattern matching is. Then we return that first element and then concatenated with this take while function. What this does is you give it a list and a predicate. So in this case, it's equal to x. So this has to be something that evaluates to a Boolean, so true or false. So something like, like a statement. So like 2 + 2 = 4 type thing, rather than like a function or a variable. So yeah, this has to evaluate. So it takes a predicate and a list, and it checks the elements in the list, and it keeps going until it finds the first element that this predicate fails on, and then it quits there, returns what it has so far, and forgets about the rest. So what this will do is we'll put x, and then this function will return, it will look at x's, so the rest of the list, and will return every element that is equal to x until it finds one that isn't equal to x, and then it'll terminate. So in this case, with the 1, 1, 1, 2, 2, 2, so this 1 would be the x, then it would look at the rest of the list, which would be this. It would be like, yep, 1 is equal to 1, take that. 1 is equal to 1, take that. Ooh, 2 isn't equal to 1. So this would evaluate to a list with a 1 and a 1. So we have that, and then we concatenate that. So then this whole thing evaluates to the 3 ones in a list. Then we recurse the function, but this time we use drop while. So drop while is the opposite of take while. So take while keeps going in the list until it finds an element that returns false with the predicate, and drop while keeps going until it finds an element that doesn't, it keeps going from the start of the list until it finds an element that doesn't satisfy the predicate, so it doesn't return true with the equals x, and then it gives you the rest. So the drop while says, we'll look at this list, so x's, remember, is all this. So it'll look at the first item and be like, yep, 1, that equals x, because x is 1. 1, that also equals 1. And then, so it'll ignore those two, and they'll be like, ooh, 2, yes, I found something that doesn't equal 1. So then it will just return the rest of the list. So it'll evaluate to this, which is exactly what we want, right? And if we go P9, awesome, cool. One mistake is take while, the W in the while should be capital. And I don't know why, like I didn't notice that these hadn't turned blue. Okay, cool. So yeah, so that's question 9. In the answers, there's a bunch of different ways to doing it, but I think this is the simplest. Okay, let's go to question 10. Okay, so run length encoding of a list. Use the results of problem 9 to implement the so-called run length encoding data compression method. Consecutive duplicates of elements are encoded as list NE, while N is the number of duplicates of the element E. Okay, so what this means is what we want is to take, so like with this list we gave with the like 111, 222, we want to replace these sublists of 111 with a tuple, which is in Haskell and pretty much every language is like that. And we want the first element of the tuple to be the element of the list. Oh, sorry, no, to be how long the list is. So for this example, it would be 3, and then the second would be what the element in the list is, because all the elements are the same. So it would be a 1. Also, you may remember, so in Haskell, all elements of a list need to be the same, but elements of a tuple can be different. So this would also work with strings and stuff. Okay, let's go P10. Okay, so the type signature for this is it wants a list of tuples. So let's go. So again, we need the context of EQA, which we wouldn't need if we were just counting the items in a list, but we do for this. So we're going to go. So that's what we want. So that's where it's going to evaluate to. But before that, we need so yeah, it takes in. Actually, no, sorry, that's wrong. So because we're going to use P9 in this function, so the input to the function needs to be the same. So we take in a list like that, and then eventually we'll return this. So what we need, P10 list equals. So what we're going to do is first we're just going to apply P9 to the function, sorry, to the list. So and then we're going to like write the rest of the function. So first, so let's go something new list, and then later let's go where new list equals P9 list. What this is doing is now we have this variable new list, which is the original list that's been put through P9. So new list is now in this form of that. Cool. So now we're going to use a helper function. So P10 dash. So okay. Might not be the best way of doing this. P10 okay, we'll do the base case here in a sec, but so P10 dash, So that takes a so this x's, x is a list because x here is going to be the output of P9, which remember is in like a list. So x is, a list where all the same element. So what we want to do is count. So we want x to equal tuple where the first element equals where the first element is the number. So let's go length of x. And the second element is the like any of the elements of x. So that takes the first element of x. Okay, so this is the tuple that we want to end with. So now, and then for the recursion, now we want p10-x. And for the base case, usually do the base case first, but sometimes I find it easier to do the recursive first. If it's the empty list, we want the empty list. Even though this might not work because the empty list isn't. Oh no, sorry. Whenever you have a list here, the empty list is like anything. So even though this is like a list of tuples and stuff, the empty list is still technically a list of tuples, just an empty one. Okay, so I think that'll work. Okay, so if we go, this should return a list with two tuples that say 3, 1, 3, 2. Hey, okay, cool. So as you can see, that P9 is doing a lot of the heavy lifting, and then P10 is just counting the elements of the list and then putting it into a tuple like this. This is how you do like the first element in Haskell. Like in Python, you do it with brackets and stuff. Okay, cool. Well, first 10 problems done. Let's see if we can push our luck. Modified run encoding length. Modify the results of problem 10, okay, in such a way that if an element has no duplicates, it is simply copied into the results list. Only elements with duplicates are transferred as NE lists. Okay, so this is saying that if instead of a list like that, what if there's a 3 in the middle? So it doesn't want us to put a tuple that says like just 1, 3. So letters would probably be easier to demonstrate this with, because then you can tell when I'm using a number and when I'm using an element. Okay, so so my first idea of how to do this is to just copy P10 and then just change it so that if X is just has like one element in it, just return that element. Ooh, this is interesting. So in the Haskell example, they're using this multiple for single B. So they're creating a data type specifically for this, which makes sense because otherwise, if you returned a list, then it would all have different elements. Sorry, the elements would be of different types, and that wouldn't work. So yeah, okay, let's do that. So data. I can't think of a better word than output. Okay, so it's either a multiple, and then an int, and then, or it's a single. What this is saying is there's two types of possibilities that this data output can be. So it can be a multiple, in which case the int counts how many of the A there is, or if there's just one, it's just a single one. And the reason why we put it like this is so that because the function always needs to return the same type. So if you have a function that sometimes returns a list and sometimes returns an element not in a list, that won't work. Like you can make it work with like monads and stuff, but who has time for that? Okay, so let's go P11. 11. Okay, so now we're still taking in a list of A's, but we are returning a list of is output already a word? Is that what's going on there? Oh no, that's cool. Yeah. It just highlights blue if it's, yeah. Okay, so we now have output. So now we still want to run the list we get through P9 so that it puts it into this form. But then we just want it such that if, okay, so let's copy this line. I think what we want is just if X, so the pattern I'm matching here is that if X just has one element, then we want it to equal single X. So single here is the data constructor, maybe type constructor, not data constructor, data constructor, I think. So then that transforms X into single X. So it's now a part of output A, so then it, yep. And then we still want to recurse on the rest of the list. And then also we need to swap these lines because I need to get my Emacs on and use all the fancy key stuff. I'm like, sorry, this is very slow. So the reason why we need to swap those lines was pattern matching works in order, so it goes from top down. So because X, if X is one element, then X will still, like, yeah, if X is a one element list, then X will still match to that, and so this pattern, like this line, will trigger. So like this is a more general version of that, because this is saying if X is just one element long. So this needs to be first. Okay, and then we're just going to change that. to multiple, and then this int, which is like before, the length of x, and then a is. So this is exactly the same as this, except instead of a tuple, by putting in these things, we're putting these two brackets so that it evaluates. Maybe these brackets you don't need. Oh no, yeah, no, I think you do need these brackets. Like I think it would error if you didn't have them. And so this length x is evaluating to an int, so that becomes the int there, and then this first element of x becomes there. So also, we actually don't need to change this p10 because the p10 with like a where clause, so the function p10 is defined like within this function, which means it doesn't cause name issues with this function. But just for sanity, we are going to change this p10 dash to p11 dash. That would still work if we didn't, I'm fairly sure. Yeah, let's try that. Okay, so ooh, so close. Oh, did I not load the thing? Oh, no, okay. Okay, cool. So, yeah, that was a silly mistake. So, when you derive a new, sorry, not derive, when you create a new data or type like this, you need to tell Haskell how to show it when you like print it out, like if you want it to appear here in the terminal. So the way you do that is just deriving show. If I wanted to compare multiples, I would also derive like EQ and stuff. So like if in another function, I want to check whether two outputs are the same, like whether they have like say the same int or something, then I would also need to put a deriving EQ. So yeah, okay, and that should work. Yeah. Okay, yeah, multiple through 1, multiple 3, 2, single 3. Awesome. Okay, problem 11 done. Okay, so problem 12. How much? Yeah, well, we won't get up to problem 20, but yeah. Okay, so again, this seems to be based on the previous two functions. So decode a run length encoded list. Give a run length code list generated as specified in problem 11. Construct its uncompressed version. Okay, so basically, this is saying to reverse this function. So turn this function, like you have this function takes in a list of elements and outputs this multiple single list. And now we want to take in a multiple single list and put out the original list. So yeah, just like this function in reverse. So that also means we're probably going to need to make a reverse version of P9. Okay, so first things first is so because we're reversing the function, that means we just reverse the type signature, right? So this function takes in a list of A's and outputs a list of output A's. That's such a bad name. I'm sorry, guys. And so what we want to do is take in, so we still want EQA, I think. Yeah, definitely. So we want to, nope, no. So we want to take in a list of output A's and take back the original list. Okay, so I think what I'm going to do here is create the reverse P9 in a where clause. So we're just going to go P12 equals P12. So yeah, we're just going to make it very similar to this. So dash. And then we're going to go where. So new list equals reverse P9 of list. What's cool is that you don't need to, when you have a bunch of things you want to define in a where clause, you don't need to like nest them. You can just go like, I don't need another like indented where. I can just go. Okay, so now we need a reversed version of P9. So this. Oh, okay. So this is actually, I think, going to be easier because all it does, because we don't need to check whether the elements are the same or not, right? So all we need to do, like, because we just are unpacking the list of lists into like a whole list. In fact, what we can just do is have reverse P9 equals concat, which is exactly the function that already has. What's also cool is if you're defining a function as like another function like that, or if you're like as a composition, you don't need to put the argument here. You don't need to go like x. You can just do that, and it's the same thing. Okay, so we could just do concat, but because this is educational or whatever, or at least educational for me, I'm going to force myself to write a concat function. So how do we start with writing a function? With a base case. So if it's given an empty list, it gives an empty list. If it's given and we're going to use the same trick here. So or are we? So yeah, let's go. This is a kind of embedded. So I'm doing like the pattern matching in like a pattern match inside a pattern match, and then equals. So x. So this is a list, which is inside this list of lists, and x is an element. So what we just want is actually, or do we just want? Yeah, no, that's what we just want is x, and then reverse PG P9. So we take that first element and just put that as an element with this cat. So eventually it'll be placed in this list. And then we just put excess back into y's. So we've taken the first element out and put it back in. We do just need one more for the situation. Where, so in that case, we just want, so that first list is just one element long, which will be eventually because this recurses, and we just want x. And I think that works. Okay, so that's that reversey thing. Now we also just need, now we need to define p12 dash, which again we can do in the same where clause. So p12 should be, okay, so p12 dash, actually maybe this was wrong. Like maybe, oh yeah, so I think, yeah, sorry. So I was reversing the functions, but I was still keeping it in like the order that the functions are. So we actually want to turn we want to turn the function back into, we want to turn the input of this multiple a single b back into a list of lists before we then reverse it. Right? 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 Yeah. So actually, I think what we want is, also reverse probably isn't the best name because I'm not reversing a list. I'm like just doing the inverse. So maybe inverse of P9 would be better. Like how sometimes I'm like really focused on what the name should be, and other times it's like, oh, output. Yeah, sure. It's an output of a function. And then this, I think, should be actually, let's make that inverse of P11 because that's what it is. Just in the same way that this is the inverse of P9. Or do we also need an inverse of P10? Oh, it's so hard. Oh no, because no, we don't, because P11 is a copy of P10 just with the, yeah. Okay, so that's fine. So let's go. Okay, so again, we're just reversing this. So P11 takes in the list of lists. We just want this bit. So it takes in a list of lists and it puts it into the multiple singles. So we want to take multiple singles and put them into a list of lists. So okay, so the two possibilities are that inverse P11 takes in an empty list, or inverse P11. So it could take an empty list, or it could take in a list where the first element is a single x and the rest is x's, or it could take in an element, it could take in a list where the first one is multiple. Pattern matching, cool. Multiple n x. Okay, so if it's an empty list, what do we put? A reverse list. Sorry, I mean the empty list. If it's a single, then we just want it to return in a list, because remember that's the opposite of that. Like here we take in a list with just x and put in the single, and then here we're doing the opposite, and then we recurse the rest of the list. And here, so here we want a list of x that is n long. So what we want is I think, yeah, to like repeat. Okay, so I think it's, we want repeat. Add it, so that's an infinite list, and it takes the first n. Testing this. Okay, so this works. This should give us 5 ones. Oh, nope. Okay. Okay, wait, what's the t? Oh, yeah, no, sorry, that's dumb. But repeat only takes. Okay, and we're back. So yeah, so what we want is a combination of take and repeat. So repeat will give us an infinite, so like a repeat 5 will give us an infinite list of 5. So what we need to do is go take 5 from like that. That'll give us 5. I think that would also work if we just went like that. I think maybe that is easier to read. So let's go. So this x comma x dot dot will now produce an infinite list of x's, and then take n, we'll take the first n of them. Yeah, cool. And then, so that turns multiple nx into a list of that's n long, all of x's, which is what we use to produce it. So, and then we just recurse. Okay, I think that should work. Can match exactor type all with actual type output a. Oh, sorry, I forgot to. That's dumb. Okay. Reverse P9. Oh, yep. Yeah, okay, so I didn't change these. And I didn't change. Oh, and that needs to be capital. Okay, third time's the charm, fourth time, whatever. Oh. New list equals inverse P11 of the list. Interesting. So it's telling me that inverse P11 only works if A is an enum, because which I don't think is true. Like, I know n has to be an enum, but x surely could be like letters or something, right? Because if I go like take 5 from yeah, exactly. Okay, and it works. So what's cool about this is that to test it, we can just go P12 and then brackets, because this is a reverse of P11. We can just go 11 and then test it as if we were testing P11. And P12 works, and this will just output that same list because they're reverse. Hey, okay, cool. So that worked. Okay, I'm gonna come back there eventually and see why this needed to be none. But for now, let's move on to problem 13. Implement the so-called run-length encoding data compression method directly. You don't explicitly create the sublist containing the duplicates, as in problem 9, but only count them. As in problem 11, simplify the result of the list by replacing the singleton list 1x by x. Okay, so I think this is saying to redo P11, but without an intermediate thing. So without turning into a list of lists, which I think I know how to do. It's interesting that they're telling us like how to implement the function, not just like how to do it. Sorry, I mean just not like to do it, but like, yeah. But cool. Okay. So P13. So because we're duplicating P11, it should be just the same type signature. Okay, so what happens when we give it the empty list? It equals the empty list. Then so when in doubt, just start with this. Like every function that uses like lists and recursion has a very similar pattern to this. Okay, so the hard part about this is we want the first element of the output A to be of type output, so either a single or multiple. But if it's a multiple, then we need to like update it. So what we're going to need to do is go ooh, okay, so this is going to be similar to the whole this take while. Do you remember the problems we were having with P9? This is going to bring back memories. So what we want is to create an output with the x, so either single or multiple. And then we want to update, and then if the next element from xs is by itself, we want to like update the output so that if it's a single, it becomes a multiple. So yeah, cool. Okay, so we're going to need a helper function. So what I'm going to do is create. We're going to have two lists, and we're going to transfer them from one to the other as we go. So the reason why we're doing this helper function thing is because for the idea I have of how to do the recursion, we need two lists, but we want P13 to only take in one list. So the way we handle that is by making this helper function that just takes in two lists and starts with what we want it to start with, like the empty list. Okay, so if both lists are empty, then yeah, we want the empty list. If the first list is that and this is empty, then we want to get rid of this x and transfer it to there and make it a single. So then we want P13 dash. So we're putting it back into this function. So this is going to be the only function, the only call of P13 that doesn't recurse back to itself. So this will be, so this is the base step, and then that'll output the eventual list. And that's why these are all going to need to have two arguments, like both of these lists. But at the very end, when they're both empty, we just return the empty list, which is then going to like wrap around the rest. Okay, so we're getting this x, which means for the first position, we're just going to put in x's. And then in the second position, we're going to put, okay, so because this list is empty, we're just going to go a single x. So at the first call, we're taking the first element, making it into a single, and putting an x. Then here's where things get interesting. So here we're looking at the first element of the list we're given and the first element of the list that we're slowly building. And if they're the same, if the single x is the same as this x, then we want to change this into a multiple. So what we want is P13 x's, yeah, and also this should be a wildcard, sorry. Because yeah, there'll never be a point where they're both empty, but it's when this one's empty that we need to output that. So P13 x's equals okay, and we need a guard here, so so if actually, yeah, let's just go so let's say this first element is a single x. Then if x, these should be y's so that we don't get mixed up. Okay, so what I'm saying here is that if we have this list that we've been given and this list that we're building, and that the first element of this list that we've been building is a single and is a y, and then x equals y, then what we want is for it to equal, then we want to turn this single, so the first element, into a multiple, right? So it's like adding on. So then we want P13 x's, and then the second should be multiple 2 x or y because they're equal. So what they're saying is we've turned this single in now to a multiple, and remember this int counts how much, and because it's a single plus 1, so it's now 2 x, and then put it back into y's. If it's not, so if they're different, then what we want is to so if they're different, then we don't want to add a multiple, we just want to add another single, right? So so we're putting the y back into the list, and then we're putting the x back into the list in front of the y. Okay. Now, final possibility is P13 dash. What if this is a multiple? So in that case, we go x equals xs. multiple n y's. In that case, x equals y. So if x equals y, then we want to increment the n up by 1, right? Because multiple counts. The n counts how many like y's there are. And so if x is the same as y, then we want to increment that up by 1. So then we want so we just want that. That could be a y, it's okay. And then we want to change this 2 to n plus 1. Okay. And then otherwise, if they're not the same, then we want t 13 dash. These should all be dashes, by the way. T13 dash to be the same as this otherwise, except that this should be a multiple. So we want that, except we don't increment n, and we there. Whew, okay, that was a long function. But hey, like that's like what we were meant to do was like they were like, hey, do this without using an intermediate function. So obviously the function we do is going to be longer if we can't break it into 2 different functions. Okay, let's check if this works. So close. Error on. Oh, this. I forgot to put the where clause. Oh my god. What a silly person. Okay, cool. Okay, so normally for the base case, you want an empty list because you're eventually like you're making a list like series of concatenations like that, right? And you want it to end with the empty list. But for this, we want we just want to return the final list because that's what we're building. So that. Couldn't match type output A1 with expected type output A1 to output A1. Okay, I'm just going to quickly put a type clause, sorry, not type signature. Dash. Okay. No, actually, no, that should. So it takes in an output, an A, and an output A. Okay, I'm not sure why this isn't working. Maybe I just have to put more brackets everywhere. When in doubt, always put more brackets. Okay, nope, that wasn't it. Okay, so dumb. Okay, so basically I just forgot to write that. Because, yeah, for the request step. So yeah, that was just a silly mistake. Hello. But yeah, that's cool. I'm like recording a video, but I'll stop now.
Do you mind if I stay here?
No, that's totally fine. Yeah. Okay, cool. See you next video.